intelligent mobile robots. How machine learning and next-generation robotics revolutionize industry. Marco Hutter, ETH Zurich.
On November 9, 1989, I was a small child when the Berlin Wall came down, and the images from that time seem almost alien. Yet they remind me to appreciate the abundant freedom I now enjoy in both my personal and professional life.
Imagine robots with the mobility and versatility of humans or animals. Systems that overcome obstacles very easily, that can navigate to arbitrary environments. You can have systems that you can send anywhere to help humankind in taking over some of the dirty and dangerous jobs. You can take them with you on a hike to the top of the mountain, but you can also send them down to mines 1,000 meters underground to take over some of the nasty jobs that you have there. Or they can support first responders like firefighters in their risky jobs. We can station them on offshore facilities to make sure that they run permanently. Or if you have a nuclear power plant or other areas that might be contaminated, you can use robots like this. And probably in the not so far future, they're going to help us in exploring and potentially preparing for settling on Mars, Moon, or other planets that we find out there. This vision has fascinated me since about 12 years when I started my research, building together with my team electrically actuated quadrupedal systems. First, this was really in a laboratory environment, just understanding the basic principles. We again had the chance to robustify that and eventually really convert that into systems that today are used in the industry for industrial inspection and other tasks. And as you can imagine, some of the big challenges when doing this is that these systems have to be able to move, to locomote. And that's the challenges that we're tackling with my research team. We're doing this using machine learning-based technologies. So these robots that you see, they're only controlled by a neural network, which gives the actuator command based on state information and observation that these robots make. And they're trained using reinforcement learning. So what this does, it's kind of optimizing that the system has to move forward, should not fall in order to robustify this. Now, if you want to train these neural networks, this needs a lot of data. And you don't want to collect this data on the real system because eventually you're going to destroy them. So what we're doing is we're creating synthetic data. So using simulations. And today we're able, on a simple laptop, to simulate thousands of robots in parallel, which means you can generate data in very short time and by that train these robots. And this training is just like a game. The better the robot becomes and the harder you make the challenges. So when they master the next level, you make it harder and harder until eventually they're able to walk over all kinds of challenging grounds that they may face in the real world. This is uneven grounds, this is stairs and steps and other obstacles. Now there's a couple of tricks that we have to apply in order to transfer this, what you see here in simulation, to the real world. I'm happy to discuss this afterwards over a coffee break. But I want to show you this learning process on the actual system. So we have here a robot. In the beginning, it's just like a newborn. It has no clue. It doesn't even know its own physical properties. And over time, we run the simulation, this robot starts to learn to locomote. And every 15 seconds, we send updated network parameters, so an updated policy to the system. And you see that the robot becomes better and better. Eventually, it figures out if it wants to move forward, it has to use its legs, it has to step. It still needs a bit of a hand of one of the students. But at some point, the system is able to just walk without help. And I can actually do this very robustly. If you have obstacles, you just go over it and do this in a very robust and stable manner. To do that, the system, this is Dodo, by the way. It's like one of the 4th generation of ANYmal robots. is equipped with all kinds of different computers. The other important aspect is, in order that this robot can autonomously move in its environment, it needs to have sensors. The sensors that are integrated on these robots are on one side a LiDAR, a laser sensor. This makes about 500,000 distance measurements per second. We then have distance sensors like stereo cameras all around, wide-angle cameras in the front and the back to see the environment. And if the system operates outdoors, you can also use RTK GPS in order to globally localize. Now, this localization works the following way. The robot scans its environment, and then it moves. It scans again the environment, and then we use an optimization approach in order to align these scans, and we solve two problems with that. First, we are mapping the environment, and at the same time, we're localizing the robot within this environment. And with this technology at hand, we have the ability to really go to environments which is very hard, even for humans. So we participated in a big DARPA competition, which had the goal to go underground, map, explore completely unknown environments like tunnels, cave networks, and urban infrastructure. And we sent 4 of these robots down there. That's how it looks like. This is an entrance gate to an unknown underground world. You know the robot goes in, after the first corner, connection is off, you have no chance. They have to go autonomously. So they go and explore these underground environments. And while doing that, they're facing all kinds of challenging environments. They have stairs, like in this metro station. There's cluttered, narrow tunnels. And if this was not enough, then the organizers even made it harder by pumping smoke into the tunnels, which obscured perception. And the robots have to deal with this. They have to robustly deal with these kinds of conditions. What the robots are doing in this time is that they're mapping the environment in 3D. So you see here the robot being in a storage space, and it looks at the environment and figures out various areas I haven't been before. Where can I gain new information? And then tries to navigate there by looking at the environment and figuring out, how should I navigate around these local obstacles? Should I climb that or not? And while navigating the environment, mapping the environment, we're looking at that. We have these camera streams, and in these camera images, we detect objects that we want to find. So these can be, for example, here is a rope on one of the shelves. And once we know that there's a rope there, we can then go back and tell the outside world there's a rope at that X, Y, Z coordinate with centimeter precision. Now, this technology that is here showcased in the context of a research program is something that is super useful and something I believe is changing the industry. So we know there is automated manufacturing, and that's really the backbone of our industry. We have autonomous warehousing, so you can order something today and it will arrive tomorrow. That's because we have all this autonomy in there. And the next generation of autonomy that we will see is an autonomous industry propelled by mobile systems, which don't need an environment that is engineered for robots, but they can work just in the environment as humans are doing. And as we're speaking, this is happening. So here's a couple of illustrations of these robots, being underground, being offshore. They work typically at places where it's expensive to send humans, where it might be dangerous for humans, or when the jobs are just too boring to do so. What they're mostly doing is inspection, thermal inspection, visual inspection, and acoustic inspection. So they walk around, they find, for example, pressure meters, they read out and they report back there's 0.5 bars on that vessel. They measure the temperature of everything around, and suddenly if a motor overheats, wasn't that hot the last couple of weeks, you have an early onset of a damage, so you can report this. You can listen to the environment, if roller bearings might be cracking, and you can also map it and look at the geometric changes. Here is 2 examples of this deployment in Germany, where they're autonomously patrolling on industrial facilities and conduct inspection tasks. You see in the left video that the robot essentially is trained in the, not in the physical world, but in the digital twin. So it plans the navigation path in there. It knows exactly what to do just from the computer. And then you go on the real facility to deploy it, it knows where it is, and just executes that route. And on the right-hand side, you see this inspection task going on, and eventually even not only visually thermally and acoustically inspecting the environment, but at the same time also creating a map in full 3D, which gives you a lot of information. Now that's today, but we are here to discuss what's the next walls to fall. What can we do with these robots in the future? And here is one of the walls. So what we show you here is ongoing research. How about this robot going on this box? It's a super challenging task, and we see whether this works or not. So this complete behavior is trained in simulation and executed on the real world. And we can not only train individual behaviors, but we can actually train multiple behaviors, going up, going down, going underneath something, and then combine all of that into higher level skills. And eventually you build up a parkour for this robot and just tell it, go over this parkour. And we modify this. The robot doesn't know anything about that. All it knows is it has to go straight over it. And that's what it's doing. That's in a park in Zurich. It localizes autonomously, it sees autonomously, and it controls autonomously. And I hope this gives you a bit of a glimpse of what you're able to do today and extrapolate a little bit what we're going to be able to do in the future. We're engineers. We are not stopping here, and that means we're also not here to trying and copying nature. Instead, what we're doing is we're building systems which may have superhuman locomotion skills. Think about this. We invented wheels a long time ago, and that makes us extremely efficient, and we go a lot faster. So what we did here is let's just combine these capabilities with the wheel capabilities. Make something that profits from both. It can locomote, it can drive, it can go very far, it can carry objects around, but it can also overcome obstacles like stairs. And actually, the nice thing with these kind of systems is that they're able to do new things which wasn't possible in the past. And eventually, if you have these capabilities of being able to move around and doing this robustly, you can actually go down and do this very robustly. So down. So we have here one last demonstration that we're going to show you. Hopefully, these robots in the near-term future, they're going to help us if we have to tear down the next walls. Thank you very much. Thanks. Thanks a lot.